Welcome to this explainer. Okay, just take a quick second and look down at your phone or your laptop. Or maybe just think about the absolutely massive data centers powering all the artificial intelligence systems today. It's honestly awe-inspiring, right? And the crazy thing is, every single one of those systems relies on the exact same incredible microscopic concepts to process data. So today, we're going to uncover the amazing journey of how a raw piece of silicon is transformed into the beating heart of modern computing. So how can billions of tiny switches actually become a working chip? Okay, let's dive into this because this is the core mystery we really need to solve together. I mean, how do we scale up from one microscopic building block, something literally smaller than a single human cell, up to billions of these components working together flawlessly to run an entire operating system? Well, we're going to take a micro to macro approach here, starting right at the physical level and zooming all the way out. Here's our roadmap for today. 1. The microscopic switch. 2. Logic gates and CMOS. 3. Building the processing engine. 4. The VLSI design flow. And 5. Physical design and verification. To really ground us, what actually is VLSI? Well, the IEEE defines Very Large-Scale Integration, or VLSI, as the foundational paradigm for modern computing. It's basically the art and science of integrating hundreds of thousands or even billions of transistors onto a single integrated circuit. It's not just one step, It connects device behavior, circuit design, verification, fabrication, and physical packaging into one seamless, massive engineering reality. Section 1. The microscopic switch, starting with silicon. Before we even get to software or any sort of logic, we absolutely need a physical material that lets us control electricity. That's silicon. By meticulously engineering silicon, we can strictly control its electrical behavior, and that gives us the transistor. Intel describes transistors as microscopic switches that form the absolute foundation of modern computer chips. Now, I want to clear up a super common beginner mistake right off the bat. A single transistor does not perform complex math. It doesn't calculate anything on its own. It's literally just a semiconductor device acting as a microscopic electrical switch. It only does one thing. It controls current flow. And that simple switching behavior is exactly what makes it so incredibly powerful. By turning the switch on, current flows, which gives us a high signal, and we represent that digitally as a 1. By turning the switch off, current is restricted, giving us a low signal, or a 0. This simple transformation, taking raw electrical current and turning it into the 1s and 0s of digital logic, is where computing actually begins. Section 2, Logic Gates and CMOS, where we start combining those transistors. Since one transistor acting as a single switch isn't even close to enough to run a computer, we have to combine them to create logic. To do this efficiently, the entire industry relies on a technology called CMOS. That stands for Complementary Metal Oxide Semiconductor. This uses complementary networks of NMOS and PMOS devices. Think of them as two different flavors of silicon switches that work together as a tag team. Why complementary? Well, because working together, they use incredibly low static power in their steady state, but they still allow for super high integration density. For example, by combining a PMOS network and an NMOS network, we can create an inverter. That's just a simple logic function that flips a 0 to a 1 or a 1 to a 0. By intelligently arranging these CMOS networks, we create our fundamental logic gates. We get our NOT gate, or inverter, our AND gates, our OR gates, and critically, the NAND gate. The CMOS NAND gate is a perfect example of a foundational building block. By combining multiple transistors into a NAND gate and then combining multiple NAND gates together, we can start creating larger, much more complex digital circuits. It's like building blocks. Section 3. Building the processing engine, taking it from gates up to architectures. So we've combined our logic gates to create functional blocks, right? Things like the ALU, or arithmetic logic unit, which does the actual heavy lifting, the addition, subtraction, and logical comparisons. But an ALU needs a place to hold intermediate information while it's crunching those numbers. That is exactly where registers come in. Built from latches and flip-flops, they provide immediate, super fast storage. We also have cache for larger, incredibly fast memory access, and a control unit to act like an orchestra conductor, managing the whole process. With all those blocks working together, we finally get a CPU. The IEEE breaks down the fundamental CPU cycle into 4 really elegant steps. You fetch the instruction, decode it, execute the operation using the ALU, and write the result back to the registers. But here's a thought. How do all these millions of tiny components stay perfectly synchronized without just dissolving into pure static? The answer is the clock. The clock provides a strict, constant timing reference. On a clock edge, data is captured, then the computation happens, and exactly on the next edge, the result is captured. This precise, microscopic heartbeat is what keeps chaos out of the circuit. Section 4. The VLSI design flow, or how human engineers actually build these chips. So, the absolutely crucial point here is busting a massive myth. A lot of beginners kind of think a CPU is just software, or that software magically does math in some invisible ether. But the fact is, software merely provides the instructions. The processor is completely 100% physical hardware. VLSI spans everything from that high-level architecture all the way down to the physical silicon packaging. We understand the conceptual building blocks now, but human engineers obviously don't sit there and draw billions of transistors by hand. That would be impossible. Instead, they rely heavily on electronic design automation, or EDA tools. This hierarchical design flow takes an idea all the way to tape out in very specific steps. You start with the specification, define the architecture, write the RTL, run synthesis, move into physical design, and finally run verification. Let's really take our time here and look at a few of these crucial techniques in depth. RTL, or register transfer level, is honestly incredibly fascinating. Instead of drawing tiny gates and microscopic wires, VLSI designers actually describe the behavior and the structure of the digital hardware using code. They use hardware description languages like Verilog or System Verilog. Think of it kind of like writing a highly specialized if-then statement. If the clock ticks, move data from register A to register B. They are coding the behavior and the logic itself, not drawing the physical wires. Once that RTL code is thoroughly verified, we move on to a complex technique called synthesis. The EDA synthesis tool acts almost like an automated genius translator. It takes your abstract hardware code and maps it directly to a library of standard cells provided by a manufacturer. You can really think of these standard cells as pre-manufactured digital Lego bricks, your AND gates, OR gates, and flip-flops. Synthesis literally translates abstract-coded behavior into a hard, physical blueprint of actual logic gates. Section 5, Physical Design and Verification, bringing us into silicon reality. Now, this is where our digital logic becomes physical reality on silicon. It's a phase heavily emphasized in advanced curriculums like NPTEL's VLSI courses because of just how incredibly complex it gets. Physical design relies on several really deep techniques. First is floor planning, which is exactly like city zoning. Engineers decide where massive macro blocks like memory will go on the silicon real estate. Next is placement, which is literally dropping the millions of tiny standard cell houses into those designated zones. Then comes CTS, or clock tree synthesis. Think of this as the insanely complex plumbing, ensuring that the clock signal reaches every single house at the exact same microsecond. Finally, routing paves the billions of microscopic highways connecting them all together. It's a giant puzzle optimizing for timing, power, area, and congestion. Now, what's really interesting here is that a circuit can be logically flawless but still fail completely due to physical timing. Enter static timing analysis, or STA. STA is a technique that meticulously checks for critical violations. For instance, if a signal traverses its microscopic highway too slowly, kind of like a turtle, and arrives after the clock edge is fired, that is a setup violation. Conversely, if a signal races through too fast, like a rabbit, slipping away before the clock edge can properly capture it, that's a hold violation. Analyzing and fixing these thousands of timing paths is literally the ultimate puzzle for VLSI engineers. Before a chip can actually be sent to the manufacturer, a massive milestone known as tape-out, it has to undergo rigorous physical verification techniques. First is the DRC, or Design Rule Check. This makes sure the physical layout doesn't violate any manufacturing rules, like ensuring two wires aren't placed so close together that they'll literally melt into each other during fabrication. Then there's LVS, Layout versus Schematic, which guarantees that the physical maze we just built actually matches the original intended logic. Finally, PEX, or Parasitic Extraction, evaluates the unintended parasitics. That's the electrical friction and resistance that naturally happens when wires get this impossibly microscopic. Only when all of these checks pass with flying colors is the chip finally ready. To understand just how vital this field is right now, I want you to consider the number 36. As of June 2026, the government of India actually reported that 12 semiconductor manufacturing units and 24 semiconductor design companies had been approved for fiscal support. That is 36 new major entities in just one country's booming ecosystem. It's absolutely amazing, and it perfectly represents the massive, growing real-world application of the VLSI design flow we just explored.
So, let's look back at the grand narrative arc of this explainer. The whole hierarchy builds step by step. We started with a single piece of silicon engineered into a simple transistor. We grouped them into complementary CMOS logic gates. We linked those together to make digital circuits. We combined those circuits into functional blocks like the ALU. We orchestrated those blocks into a complete processor. And finally, we integrated that processor with memory and interfaces to create an entire system on chip. That is exactly how billions of microscopic switches become a working chip.
We have covered an incredible amount of ground today, from physical devices all the way up to deep physical verification techniques. But, there's always more to uncover in this amazing field. So my question for you is, which should we dive deeper into and explain next? The physics of the MOSFET, the intricacies of CMOS logic, or the behavioral coding of RTL? Think about it, and keep exploring the incredible world of VLSI. Thanks for joining me on this explainer.